Hello, AP Physics students. This is Dr. Brinzi here, and this is lesson A.4. This is our fourth and final lesson on fluid dynamics. And in this lesson, we're going to actually be able to explain how the flow of an incompressible fluid affects its pressure. Up until this point, we've been talking about fluids that have been static. In other words, they have not been moving, but today we're finally going to study fluids that actually move. Alright, so let's go ahead and get started. I have to start off by talking to you about ideal fluids. We have to make some assumptions here in order to get equations that look nice and neat. If you were to study fluid dynamics in any more depth, you'll study fluids that are not ideal, but that's not that's beyond the scope of this course, basically. So, ideal fluids are, number one, incompressible, which means the density remains constant. Okay, we talked about this in a previous lesson in this unit, and incompressible fluids apply generally to almost all liquids or most liquids. And they also apply to gases that are traveling well below the speed of sound in that medium. So, even though air is generally thought of as a compressible fluid when you're talking about pressure versus height, for the purposes of fluid flow in in a small area, you can think of that that air, as incompressible. So you can treat it as incompressible. The other thing about an ideal fluid is that it does not have viscosity. And viscosity can be thought of as internal friction between fluid particles that cause the fluid particles to slow down. If you were to study fluid dynamics in any more depth, you might come across the word inviscid. That just means without viscosity or viscosity free. So these two properties of ideal fluids we need to understand in order to come up with some equations that we can use. Okay, now there are generally two types of flows that incompressible fluids, or ideal fluids, can undergo. The first type is what's called laminar. And the word laminar, it comes from the Latin word lamina, which means thin sheet. So if you look at this air test of a car, you'll see that the airflow comes in nice thin sheets that stack neatly on top of one another, and they always stay stacked on top of one another. And this laminar flow has no abrupt changes to its velocity. In other words, we're not suddenly taking a left or right turn or an upturn or a downturn, so that it's nice and continuous. That's another way to think about it. And it remains constant over time. So this flow 5 seconds later would look very similar to what it looks like in this snapshot. Now, the other type of flow that we're really not going to study, but you need to be aware of, is what's called turbulent flow. And turbulent flow can be thought of as very chaotic and changing with time, which means it's not steady state. Okay. If you think about the heat rising off of a hot air rising off of a street on a hot day, or you could think of smoke coming off of a cigarette or something like that. What you'll see is that flow changes constantly with time. It changes, and it doesn't seem to have any sort of predictable pattern. And therefore it's not a steady state flow. And we're not going to concern ourselves with this type of flow. Okay, so let's talk about steady state flow. you can define what are called flow lines, and we actually saw this in the picture of the car that had air flowing over it. A flow line is a path of an individual particle within a fluid. So if, like say, we have a particle, let me pull my pen up here. If we have a particle start right here at this moment in time, then later on in time it will stay on this flow line over time, and I can actually trace the position of that particle over time, and it will make a nice line like that, and that's what we call a flow line. And then if I take a bunch of flow lines that pass through some sort of cross-sectional area, so this right here is a cross-sectional area. I'll color that in. Okay, so all of the flow lines that flow through that cross-sectional area, A, make a flow tube. So you can think of this as a big tube that is moving from here up to here over time. Okay. There are some rules that steady state flow follows. Two of them in particular I can think of. Rule number one is that if a particle is on a flow line, it will always be on that flow line. So this particle right here is never going to jump off of this flow line over time. So once I know that it's on this flow line right here, I can predict that over time it will always be somewhere on this flow line. Okay. So it's not going to suddenly jump down to another flow line, like say this one way down here. It's never going to jump over to that one. Okay, so that is one rule, and kind of like it's a corollary to it. Let's say that I have let's say that over time this particle moves from here to here. Then if another particle comes by and it's on that same flow line, so let's draw a blue particle that comes by, that blue particle I know will also end up staying on this flow line as well. So it's going to follow the direction of the red particle. So that's kind of like a corollary of rule number one there. The second rule of steady state flow is that flow lines never cross one another. And you could definitely see that in the picture of the car. Those lines of smoke never actually cross one another. They compress closer together, they grow further apart, but you may have noticed they never cross one another. So that is a second rule of ideal flow, is that those lines never cross, which is really interesting. Okay. Also got to define for you these things called flow rates. And flow rate is, let's talk about volume flow rate first. And it's how much volume passes through a cross-section per second. So if I have a cross-sectional area A here, okay, so I cut out this cross-sectional area inside this flow tube, and I want to measure how many cubic meters of gas or fluid, have passed through there in a given second. Then I can calculate that by taking this area A and multiplying that times the velocity that fluid travels. And that will tell me how many cubic meters flowed through that tube, or that cross-section, how many cubic meters flowed through that cross-sectional area A in a second. So I just need to take the area times the velocity of the fluid. The mass flow rate is how much mass passes through that cross-sectional area per second. And all I need to do is multiply the volume that flowed through in 1 second times the density of the fluid. So mass flow rate is just volume flow rate times density. Okay, now I've had to define a lot of terms for you here and give you a few definitions and some very basic equations. But now the equations are going to get a little bit more interesting, but they also get a little bit more difficult. There are two equations that we can use when we talk about flow in an incompressible or an ideal fluid, excuse me. One is what's called the continuity equation. So in an ideal fluid, the volume flow rate is conserved. In other words, that volume flow rate never changes. So if I have some sort of fluid or flow tube that suddenly, well, actually I shouldn't say suddenly, but that has a that compresses itself or pinches itself, what I know about that fluid is that the amount of fluid that flows through this cross-sectional area A in a second has to equal the amount of volume that flows through this cross-section A here. Okay. So as long as I have the same flow tube, so I'm taking the same flow lines, okay, the cross-sectional area A for that flow tube, and another cross-sectional area A later on, then in an ideal fluid, that volume flow rate in that flow tube has to be conserved. And so we can say that A1 times V1 is equal to A2 times V2. Now, because the fluid's incompressible, we can actually say that mass flow rate is conserved too, and that just means that we multiply both sides times the density of the fluid, right? So I didn't bother to actually write that equation down here because very much more often we use these, the volume flow rate continuity equation. Okay, so that's one of two equations that we use. Now, the second one, I could just write it down like I wrote down the continuity equation, but the continuity equation is fairly straightforward to understand. It doesn't take too much intuition to grasp it. But the next equation actually takes some setup to understand how it works. So I'm not going to give it to you right away. I'm just going to tell you the name of it. And then we're going to actually talk about how it works. And I really want you to grasp a deep understanding of how it works. So that equation is what's called Bernoulli's equation. And is named after the person who first formulated it way back in the, I believe, 18th century. And that was, his name was David Bernoulli. So I want to start setting this up by asking, first of all, what happens to the kinetic energy in this fluid? So there's a certain amount of volume that flows through this section of the flow tube. And let's say that in some time, little dt, so some very small amount of time, dt, this is the amount of fluid that flows through the cross-section A. And then later on, that same amount of time, little dt, we have that same volume of liquid flowing through that cross-section A2. What happens to the kinetic energy in this fluid? Well, so I can say that the kinetic energy in this section of the flow is 1/2 times the amount of mass in this fluid, so the amount of mass in that volume, times V1 squared. And at A2 I can write a similar equation. Okay, so the mass that flows through in that amount of time dt has to be equal, according to the continuity equation that we just studied. Okay, so I don't need to have an m1 or an m2, I just need to have m. But the continuity equation also tells me that A1 times V1 is equal to A2 times V2. In other words, these volumes, A times V, have to be equal. Which means that if A1 does not equal A2, then the kinetic energy of this parcel of fluid right here, this volume of fluid, does not equal the kinetic energy of this parcel of fluid right here. Well, if those kinetic energies aren't equal, then there must be something doing work on the fluid. Okay, interesting. Well, now let's think about what's doing work on the fluid. So what is doing the work to change the kinetic energy of the fluid? Well, let's think about this fluid just going from point A to point B. And we'll say that point A and point B are very close to one another. They're infinitesimally close. Now, there is pressure in this fluid, right? There is pressure from all the fluid behind pushing on it in this direction. So we can say that the amount of force that's pushing on this parcel of fluid is equal to the pressure of the fluid times this cross-sectional area A. Now, likewise, there is all the fluid on this side pushing in the opposite direction with a force FB, but that force is different because the pressure is different and the area is different. So if I have, if this area is not equal to that area, then there's a net force. And if there's a net force and this fluid is moving, then there has to be some work done. Well, let's try to figure out how much work this force does over some little time period dt. So as this fluid flows from point A to point B, how much work is being done by this force over on this side? Well, we know that work is equal to force times displacement. So this fluid is being displaced by, we'll call it dSA. So in some little time, the fluid moves from here over to here. So we can write force times displacement. Well, that force is equal to pressure times that cross-sectional area A. But this distance ds, we can write that as the velocity of the fluid times some little time element dt. So the work done by this force is equal to the pressure of the fluid on this side of the element, of the fluid element, times this area A, times the velocity of the fluid at this point, times dt. Okay. Likewise, we can calculate how much work is being done by this force over here. Now, since that force is pointing in the opposite direction, it's actually going to do negative work. And also note that this fluid doesn't necessarily go the same distance. This part of the fluid actually could go a different distance, so we're going to call that different distance dsB. So the amount of work done by this force is equal to negative FB times that separate distance dsB. Okay, so again, we can come up with a similar conclusion here, or a similar formula, that the work done by this force is equal to negative pressure, PB, times that area, AB, which is different than AA, times the velocity of the fluid at that point B, times dt. Okay. So if I want to figure out the net amount of work done, I just have to add the work done by each force. And, oh, I forgot one thing. One thing that I can do, though, is that I notice that this thing is the quantity that we had in our continuity equation. So this thing in this AB VB has to equal AA VA according to the continuity equation. So I can replace this with AA VA. And so the work that's done by this force over here can be written as negative PB AAVA times dt. Now if I add these two works, the work done by each force, I get net work is equal to AAVA dt times the difference in the pressure on the two sides. Okay. Now, that is the net work done when the fluid goes from some point A to some nearby point B. So let's write that down again. You don't need to write this down on your paper, but so in some time dt, the fluid in this cross-section area A is going to flow over here to point B, which is infinitesimally close to it. And the net amount of work done is that formula that I just gave to you. So as we flow from point A to point B, this is the net amount of work done. Now, let's extend that a moment in the future. And let's say that in the next amount of time dt, so the next infinitesimal slice of time, we actually go from point B to point C in that same time element dt, just a moment later. Well, I can write a similar equation for the net amount of work done as the fluid flows from here to here. And that will look like this. Now, one of the things I can do according to the continuity equation, let me back that up. I had this, is I can actually replace ABVB with AAVA. So let's do that. The continuity equation allows me to do that. And so if I wanted to figure out the net work that was done from going from A to C, I would have to add these two works together, okay? And what I notice is that in this equation I have AAVADT times PB, positive. But in this equation here I have AAVADT times negative PB. So what ends up happening is those PBs end up subtracting themselves out. So those cancel. And now I'm left with AAVADT times PA minus PC. And I could keep on continuing this as long as I want to. Okay. And this tells me that the net work done over that amount of time, over any amount of distance from one point to another, is equal to AA times VA times dt, some time element dt, times the amount of pressure at point A minus the amount of pressure at point C. And point A and point C don't necessarily need to be infinitesimally close to one another. They can be as far apart as I want them to be. And that will be the net work that's done on the fluid. So I just need to take the difference in pressure at the 2 points and multiply that times the cross-sectional area at where it started, times the velocity where it started, and times some little time element dt. Okay, so where are we going with this? Well, let's recap here. First of all, we figured out that the kinetic energy is changing in this fluid. So this fluid element has a different amount of kinetic energy than this fluid element does. And then what we did is we calculated the net amount of work that's done as the fluid goes from here over to here. Now what we can do is we can say, well, the amount of work done is equal to the change in kinetic energy. That's the work kinetic energy theorem, right? So if I'm going from point 1 to point 2 here, I have some sort of pressure P1 and some sort of another different pressure P2. And I can use the work kinetic energy theorem to say that the amount of work done on the fluid is equal to the change in its kinetic energy. So the amount of work done, we just figured out as A1 V1 dt times P1 minus P2, the difference in pressure at the 2 points. And that's equal to the change in kinetic energy between the 2 points. So I have 1/2 times whatever mass is inside this fluid element. So there's some sort of amount of mass in here. Times V2 squared minus V1 squared. So this fluid, if you can't see, is flowing at some sort of velocity V2. And this fluid, that same fluid element, a little bit before in time, was flowing at a velocity V1. Okay. Now, let's see if we can come up with an expression for the amount of mass inside this fluid. So mass is equal to density times volume. So I just need to figure out the volume of this fluid over some little time dt. The volume of that fluid is going to be the area times this length. So I can write this as A1, which is this cross-sectional area A, times some little length element ds1. Well, this length element ds1 is equal to the velocity times some little time element dt. So I can write that the mass is equal to rho times A1 V1 times dt. So let's replace this m with this expression right here. And this is what I get. Now, there are some similar looking terms on both sides of this equation. So I'm going to actually go ahead and divide out those common terms, which means those A1 V1 dt's go away. And now I'm just left with P1 minus P2 equals 1/2 rho times V2 squared minus V1 squared. Okay, now I can arrange these terms so that all of the 1's are on one side and all the 2's are on the other side. And when I do that, I get this equation right here. P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Okay, which means that this this term P1 plus 1/2 rho V1 squared, that is conserved within the fluid. So this thing is equal to some sort of constant. And it never changes within the fluid. I can pick any 2 points in this fluid, and I know that if I add the pressure plus 1/2 rho V squared, I know that that quantity is conserved in the fluid. It's going to equal the same amount anywhere in the fluid. Okay, now we can finally get to Bernoulli's equation here. Okay, so that was actually a simpler form of Bernoulli's equation than what Bernoulli actually came up with. So we came up with P1 equals 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Now Bernoulli added a different twist to it because he said, well, this change in pressure that causes work to be done can change the kinetic energy of the fluid, but it can also change the gravitational potential energy of the fluid. So if the fluid is flowing uphill, or if the fluid's flowing downhill, then instead of just saying kinetic energy, we can write kinetic energy plus potential energy. So what Bernoulli came up with is actually this equation right here. And this is actually just mass times g times height, mgh. Well, it's in a slightly different form. Rho times g times z, and z represents the height of the fluid. Okay, so this is actually Bernoulli's equation. Okay, and there's a picture of Daniel Bernoulli. I think I said David Bernoulli earlier. It's actually Daniel. Sorry about that. Now, okay, let's recap what this equation actually is saying. Whoops, I'm fast forwarding here. Okay. First of all, it's saying that, whoops, hold on here. Oop, there we go. First of all, it's saying that the total energy in the fluid is conserved. This quantity, if I calculate P plus 1/2 rho V squared plus rho times G times Z, if I calculate that anywhere in the fluid, it's going to be constant. So I can pick 2 points in the fluid, calculate this sum, and those two sums are going to have to be the same at those 2 points in the fluid. This equation is saying total energy is conserved. This is the amount of kinetic energy per unit volume in the fluid, 1/2 rho V squared. This rho times G times Z, that is the potential energy per unit volume in the fluid. And an interesting result is that the amount of pressure in the fluid is some sort of like internal energy per unit volume. So pressure can be thought of as an internal amount of energy. And that pressure can do work on the elements of the fluid right next to it, which is a really interesting result. We never think of pressure as like some sort of internal energy, but it is. Okay, I know that my video is already running long here, and I want to show you a couple of examples. So what I'm going to do is I'm actually going to split this into 2 different videos. So I'm going to show my examples in the next video here. Sorry about that. I know there's a lot packed into this lesson, but there really wasn't some nice, easy way to like split it up into 2 different lessons. So thanks for sticking with me, and I imagine you'll be seeing me in part 2 when I go through a couple of examples of applying Bernoulli's equation and the continuity equation to fluid flows. All right, talk to you later. Bye.